So yeah, my talk is called The Fourier Transform, a bridge between music and analysis. And one of the things I like the most about maths is that you learn very nice words, and then you can a little bit use them. So if you have not seen this sign here, this is kind of what is the sign of an isomorphism. Isomorphism is from the Greek same form. So what I will try to convey in this talk is that somehow the upper picture has the same shape as the bottom picture. There is some kind of way that if you see both pictures, you will actually be seeing the same thing. So perhaps we can start with the upper one. So this is a music score. And what we will put particular attention about this music score is that the information that is conveyed in the music score. So in particular, if you read, let's say, from left to right, you will see that this is kind of a time component. Basically, the music score is saying, like, at what time you should be playing each note. And from bottom up is telling you the pitch. Here is a little bit grave, and then as you're going up, you're going go a little bit higher. And in fact, we will hear these scales. So what I would like you now is a little bit to really put attention into these two aspects of the music score. So we will be hearing that the pitch will go higher, 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 and eventually we will reach a point when it will become again down. So let's hear a bit. OK, so hopefully this was enough for us to say that, OK, the music score has these two components, and that's fine. But OK, what's next? So perhaps perhaps you like to play an instrument, in particular, for example, the violin. And if you're learning to play the violin, then you will learn that you have to put your fingers in particular positions. And in particular here, I want you to bring your attention to this third finger C scale. So there is here the C. And well, here it's saying how you should play it in the violin. But perhaps you have friends, and your friends are learning the piano. But then you will notice something strange, perhaps, that actually your friend that is playing the piano also has a C. Now it's in a different way, because now you are playing the piano. But the note is the same, right? This symbol here is the same symbol here. So there is this natural question, like, if it's the same note, how it is that we can actually distinguish between a violin and a piano? Well, that is because there is something called overtones. An overtone is a faint higher sound that comes with a main note, and the mix of overtones is part of what makes a violin sound different from a piano, even when they play the same note. So a little bit of what we will now try to understand is what are these overtones. So here is actually a representation of the overtones that you will hear if you play a C chord. So actually, let's put a little bit in perspective what this slide is saying. In this time, from bottom to up is the time component. And from right to left, as you can see here, is the different notes that you will hear when you play this chord. Actually, what they play was these three notes, C, E, and G. So these notes were the notes played on a piano. And these from, let's say, from here all the way here are the extra notes, these overtones that give the characteristic sound to the piano that are actually present. In particular, this is kind of the first, a more sophisticated Fourier transform, but we will not get ahead of time. So here is just a representation of the overtones that actually you will hear when you play a chord, and the chord in particular is this one. So again, they only play these three notes, but we notice that that's a piano just because the note also includes all these, the rest of it. So a natural question is like, OK, the piano have these overtones, the violin has another overtones, but then what will be an instrument that there has no overtones? The pure C. What will a pure C be? For example, then you can think about instruments that has less overtones. Some of them, for example, are ocarinas and flutes. They have their little overtones. But if you start taking and taking and taking overtones, perhaps at the end you get to the idea that the good model of the C will be that, well, the sound is a vibration of the air. So you will like to hear just one frequency, that the frequency which in the air is vibrating, that is only encoding one frequency. So you don't want any other overtones. You just want one note, and that note should be the one that just one frequency in which the air is oscillating, the one that has no overtones. So just one particular note. If you do that, and perhaps you can use a little bit of math, then you will get that, for example, in this particular case, if we have an A note, that will correspond to the air oscillating at 440 hertz. So in 1 second, you will have 4,400 oscillations. So let's try to hear how this pure sound, how is this pure sound? Very nice, right? Also, I want you to bring it to your attention that this is actually a very short time, right? In terms of seconds, this is not even a second. It will be like really quick. But I think it makes, if we will see that that's because if we put a whole second, the graph gets a little busy. But just have in mind that actually this is not a very long time. So when we hear music, actually we are in scales that we have a lot of time to hear all these oscillations. Here only we have 1, 2, 3, 4, 5. But when we hear music, we are, for example, this particular note, in 1 second, we will have 440 oscillations. So again, this is A. And OK, now it's the fun part. Now it's time for the math. This is the Fourier transform in all its glory. It is an integral transform. That means you use an integral to transform a function into another function. In particular, there is this complex exponential here. If you are new to complex numbers, the way to think about them is you have a plane, and each point of the plane represents a number. So basically, you need two numbers to give one complex number. And in particular, if you put all these complex numbers in the plane, and you take just the one that is a circle with radius 1, that is what this here is representing. So this complex exponential is just representing a circle of radius 1 in a plane. And what this f is telling us is how fast are we going around the circle. If this f is really low, like really, if this f is really large, that means that we are going around the circle really slowly. If this f is really short, that means that we are going around the circle really, really, really fast. But the question is like, OK, fine, you have the circle. Why would you use it? The thing is that this circle in the complex plane is just a circle. But if you start decomposing it in these two directions, you will see that the circle actually decomposes in a lot of what these pure tones look like. It will be something that looks oscillating in the x direct, well, in the direction in one of the real components, and also in the imaginary ones. So a little bit of the intuition here is that the Fourier transform is somehow telling us how much it likes in particular a particular frequency. And we can choose any frequency we like. Sometimes the Fourier transform will tell us we like this frequency more than another one. And basically, that will work a little bit like this prism, that if we have a signal, for different ways in which we are going around the circle, the Fourier transform will tell us we like that more or we like that frequency less. So let's see an example. So we have our A, our pure tone. Notice here that it's important that the tone is just a short amount of time. So before that, it was completely silent. We have, for this very period of time, the sound, and then it's again silent. That, of course, will make eventually the function to have a jump. So that is the way in which we have our signal. So then we can plug it in, and that will be the Fourier transform of this signal. As you can see here, you have basically two oscillations, because as I said, the Fourier transform in general will be a complex number. So you will need to give me two numbers in order to have this complex number, so this point in the plane. So basically here, for each f, for each frequency, we have these two numbers. We can do that, but I think in terms of like having an intuitive understanding on what this actually is telling us, instead of actually seeing the point in the plane, like instead of thinking about them in this point, we are going to just give kind of the magnitude. How far is the point with respect to the origin? That is where we're going to be interested. And what we are going to do is actually to take the magnitude of this Fourier transform, the absolute value. So basically, what will happen is we will have a signal. Then we will take the Fourier transform. We will take the absolute value. And then we will get another function that will look a little bit like this. If you are a little bit worried about this, I will suggest that you see the Fourier transform as a black box. I will give you a signal. We will do something with it. And then you will get another graph. That will be what we will be doing the rest of the talk. So for our original tone, how does the Fourier transform, what does the Fourier transform look like? Well, it will look a little bit like this. And as you can see, basically the Fourier transform is that saying that he really, or she or it, I don't know, the Fourier transform really likes the 440 frequency. It's saying that it has other frequencies, but somehow it's having this kind of nice result that is actually picking the main frequency that we are interested, which was this pure A tone. So this is one example. Now let's try to do a little bit more examples to get intuitions. So now we'll go a little bit higher. This will be E. That will be the fifth of A. As you can see, this one oscillates a little bit quicker. So we will expect a higher pitch. And as you can see, again, the Fourier transform is actually saying, yeah, I like very much the 660 hertz. So let's see if this is actually correct, so that this is actually higher. It's still pure. This very annoying, very, very pure thing. This is higher. This is lower, sorry. This is the original A. And we have then our Fourier transform. OK, but what will happen if you play both notes at the same time? Perhaps intuitively you say, like, well, we'll have the two notes, something like this. But actually, because there are waves on air, they will actually add. They will actually change the form. And actually, the wave will look a little bit more like this. It will be a bit more busy. And it will be not so easy to see exactly what frequencies are in this wave. So let's see what the Fourier transform say about this particular signal. So if you do that, then you will notice that the Fourier transform actually also again pick the right components. It's saying, yeah, you have a little bit more complex signal, but I still like very much the 4400 hertz and the 660 hertz. So basically, with these examples, I want to at least convince you a little bit, or at least motivate, that basically if you have a signal, the Fourier transform is telling us particular which frequencies are there. Perhaps a source of confusion is like, well, here you have negative numbers. What is the deal about that? The frequency should be positive, right? We have positive. Yes, it's true. But also at the same time, the Fourier transform, as I told you, is a complex. It's giving you complex numbers. So basically, here, the negative numbers are just guaranteeing that our original signal was real. So it was a real signal with real numbers. That is a little bit mathematical terms. But also, you can see that they are pretty symmetric. So basically, you can ignore the left part of the graph, and everything will be contained on the right-hand side, because they are just a mirror image of each other. OK, so I think this is the and well, if you want to hear how it sounds when we play both together, this will be it, right? This is the both of them at the same time. Okay, I hope we are a bit together still. And now I would like to talk to you about analysis of high frequencies. So what is this? Imagine you are outside. You are with your piano, your violin, your favorite instrument. And then you want to play these two notes, these two pure notes. Then you play them. But the moment you play them and record them, then there was this very high pitch, let's say a siren, that was very, very loud. And this messed up your recording. So you're very sad because you wanted really to hear these notes when you got home. But then you remember that there was something called Fourier transform. So you asked ChatGPT or someone, or like you calculated yourself because you were really motivated. And you calculate the Fourier transform of that. And you notice the following thing. You notice that you have in your recording the notes that you wanted to, these two notes. However, you have this really horrible peak that is the noise coming from the siren. So that is like, OK, what can I do? And something that you can perhaps think about doing is just make it 0. Like, take away all these frequencies. So basically, that's what we're going to do. Basically, you will pick a particular frequency where everything to the left, you will make it to be 0. So there will be basically no high frequencies in this now, what we will call a spectrum. So this here, when you give me a signal and I'll give you this kind of graph that has the frequencies of the signal, that we'll call the frequency spectrum. So what we will do is to make 0 all that spectrum. And the Fourier transform here has this property of being a bridge because basically we are going from time, so a signal in time, to something that lives in frequency. But a bridge has the nice property that if you go from one side to the other, you can also go from the other side to the first side. So there exists something actually called the inverse Fourier transform that says that if you have a signal, if you have a frequency spectrum, then you can do something with that so that it gives you an actual signal. So if you take away all the high frequencies, basically your new signal will look a little bit like this. So on the right-hand side, you can compare with the original one. The original was these very high frequencies was kind of the noise, the annoying part. But now you have this kind of nicer one, which you have hoped that actually is containing the properties of just the two notes that you wanted from the beginning. So let's compare it. Let's see how good is actually the Fourier transform. I think it's pretty good. I will say that just by actually cutting all these kind of high frequencies, we have something that looks pretty similar. But everything that when something doesn't work, it doesn't work in the very little details. And if you put attention, in particular at the beginning of the frequency, here it starts at 0, but here it starts somewhere else. So basically, what the high frequencies are telling us, or what we lose when we just take it out, is in particular the information, for example, that we have about the jump. Remember that our original sound had a jump, and by taking away the high frequencies, we basically lost that information. So the Fourier transform is not able to kind of say that at this time you have this jump by taking away the high frequencies. So somehow the high frequencies are telling us information about the jump that we are not capturing when we are just taking away all these high frequencies. So let's do a little bit more analysis about this. This is what is called a sawtooth wave. As you can imagine, this will sound even nicer than the pure sine wave. Already you can see it in Fourier space, because as you can see, for example, this one here, as it goes down, kind of the high frequencies are not getting smaller. So are you ready? Let's see. So it actually sounds a little bit rougher, right? Like it has a little bit more discontinuities. It's kind of more like noisy. And that noisiness is coming because as we move in the frequency domain, kind of the high frequencies do not become less and less, which comparing, for example, with the pure sine tone, is extremely fast. How does that decay? So again, high frequencies, what are telling us is a little bit of how rough is the original function. So basically, the punchline of this slide is if the function is really rough, really noisy, the high frequencies will in general not become 0 as you move to higher and higher frequencies. And if your sine is very nice, very smooth, in general, your high frequencies will become very, very quickly 0 as you move to higher and higher frequencies. Okay, so the last boss of roughness, noise. So the yellow one here is actually noise, Gaussian noise. And as you can see in the bottom, this is not decaying at all as we move in frequency. So basically, this is telling us that the original sine was completely rough. However, if you smooth it, if you make it like smooth and nice, even if the Fourier transform spectrum is not nice, you can see that it decays very quickly as you move infinity because the original signal is a little bit smoother. So, of course, we will now hear a little bit of noise. And after the noise, I want you to hear what will be a bit of a song, in which after will be the song, and after that we will take away the lower frequencies so that you can compare how does a sound sounds with high frequencies and with low frequencies. So first, let's hear about the noise. Very, very noisy. And so as you can see, basically, in this comparison, when we have the high frequency, we have a lot of, for example, kind of these hi-hats. Hi-hats are very kind of noisy. They are not very harmonic, and so on. And the moment we take that away, we have this very bass sound, very, very big, long kind of stretches that does not have this kind of noisiness in them, or it's hard to think about to being noisy. OK, so this was what I want to talk to you about high frequencies. And now let's talk about time frequency analysis, because you can rightly say, like, well, you start motivating all this because you wanted to find the pure C, the C that was kind of the C that only has one frequency. And when I show you the Fourier transform, you say, like, yeah, the Fourier transform is saying that it likes this frequency, but has a lot of frequencies. So what will actually how will actually sound that the thing that only has this frequency? Like when you play the Fourier transform, only has one frequency, not saying that this is perhaps the better, but that only has one. And we will note that this is related to how long the signal lasts. So let's go back again. Again, I told you that this was like the pure C, or well, in this case, it was A, sorry. And we do Fourier analysis, and I told you, like, OK, there is a frequency that is more like by it. But still, we have this, right? So this cannot be the pure C or the pure A. There should be something that we should do with this in order to make this just to be like kind of more concentrated along this. And we will achieve that if we let the signal to last longer. So that is how we will look for 1 second. So again, part of the test, how many oscillations are here? That will be there. And it has to do with this number. But I will let you think that. But let's just, for the sake of make the slide a little bit prettier, to just have double the time. So before, we were just in 0.01. Now we will have actually a whole 0.01 second more. If we do the Fourier transform, now, if we compare actually with the original one, this is a lot more concentrated. And also, it is a bit higher. So the longer the wave lasts, the more concentrated the frequency is. So if you really wanted to hear something that has just one frequency, and that frequency will be A, for example, or 440, that will have to last an infinite amount of time. And that will last a long time. So actually, that pure C will have to last an infinite amount of time, which is not so nice. But let's see a little bit what happened in the other direction. So here, the longer we let the signal B, the more the Fourier transform likes to concentrate the frequency, more like it wants to give you precise where the frequencies are. If we go in the other direction, so if you say like, let's just take it like for a short amount of time, then the Fourier transform actually will be surprising and will say like, well, you don't even give one full cycle. So the Fourier transform will be not very comfortable to tell you that you have only one frequency, and it basically will spread all the frequencies along the, in the spectrum you will have a lot more frequencies. And this is kind of interesting because if you want to ask the question, at what time you hear these frequencies, you will say that the Fourier transform is kind of being a trade-off. Because if you want to really know what frequencies are in a particular time, that means that you want something like this. You want to say like, in this particular time, which frequencies they are. The Fourier transform kind of say like, yeah, I don't know. There's a lot of them. But in the other direction, if you have a lot of the signal, then the Fourier transform will be very good to tell you what frequencies they are. But then you don't know where do they appear, actually. So there is something called short Fourier transform. That basically what you do is basically split your signal into a bunch of chunks, and you Fourier transform each of these chunks, and then you assign kind of, by looking at these chunks, then you can do averaging or just taking the magnitude, and that will tell you which frequencies appear at what time. And this is particular an spectrogram, which one has done exactly that. You have some signal, then you have decomposed it, and then you're Fourier transforming these different chunks, and now you can represent at what time which frequencies are appearing. By the previous thing I told you, this has some kind of inherent uncertainty because you are not arbitrarily good, but this is basically what the spectrogram is telling us. It's telling us which frequencies are appearing and which times. In particular, for this spectrogram, this is the signal. The original signal is the following one. So as well, if you hear, this is kind of like the fundamental note, and because it's violin, these all are harmonics, and the color, the brighter the color, is telling us that the Fourier transform has a higher peak there. So that is, I think, a little bit of this kind of same shape that I want to bring to your attention. So we have time in one direction, and in both cases, and in one case we have frequency, and in one case one has pitch. The title, I must confess that the title of the talk was incomplete. Perhaps you thought the Fourier transform, a bridge between music and analysis. Analysis of what? High frequencies, time frequency analysis. But none of that. We are here because we are doing a little bit of cosmology and general relativity. So is the analysis of course, black holes. I think that if we are doing gravity, we have to mention that word. So if you were here for the previous talks, you perhaps have seen that there are black holes. The black holes like to come together. They start spinning. They start getting closer and closer together. They finally merge. And that is so violent, and there are so many things that happen, then the gravitational waves start oscillating, and these waves start propagating. And actually, here in the US, you have detectors. Each of these kind of arms are around 2.5 miles. And when these waves comes, these arms change kind of the length of the arm changes, and actually you can see signs of that. So these were actually the signals that were detected by these arms. And if you do Fourier now analysis and you do like, as we saw the spectrogram, actually the spectrogram looks a little bit like that. The black hole is coming together, and then when they merge, they have this really high frequency that says kind of like when do they merge. What is very kind of fun is that when you do this frequency analysis, the frequencies in which these events take place are the same range of frequencies that we hear. So one can always kind of say that, I don't know if you have heard that basically gravitational wave astronomy is kind of our ears to the universe, because the frequencies that are contained in these waves are kind of the same kind of frequencies that are the waves that we hear. Of course, I want to be very clear. These are not sound waves. These are waves of gravitational waves. They are very different types of waves. But when you do Fourier analysis, in the frequency, if you didn't know where the frequency comes from, you would very well say that, OK, this is something perhaps that we could hear. And that is why people do. And this is, for example, that one can hear, for example, black holes. And I will just show you how does this merge of black holes sound. So let's hear it. As you can see, nothing happening, nothing happening, nothing happening, nothing happening. And that is exactly when they merge. So I know we are getting hungry, so perhaps it's time to go to lunch. So I want just to finish with this. As a summary, the Fourier transform is a powerful tool for understanding time-dependent signals. A little bit like a prism, it splits, like a prism splits white light. The Fourier transform decomposes a signal in the frequency spectrum, so in all these different things. Future directions, this is more for you. Also, if you're curious, how much actually of a frequency alone reveal about the original signal. There is this very nice branch of mathematics called spectral geometry that actually deals with the question of, can you hear the shape of a drum? If you hear a note of a drum, can you tell something about the shape of it? And of course, this in the context of gravitational wave astronomy is if you can hear the mass of a black hole. If by just having the shape of the wave and the frequency analysis, can you actually say something about the mass of the black holes? And well, I'm part of the Center of Relativity and Cosmology, and a little bit of what I do is actually try to understand high frequencies in different physical situations, and how does these high frequencies tell us about physical properties. So I would like you to thank you for your time, and thank you for being here.
We want to leave a little time for questions and answers. You know, I teach English, and in literature there's this phrase, the music of the spheres, and we just heard that. It's quite literal. There is a music. There are frequencies that you can actually scale in music. Any music industry majors in here, by the way? Any music industry majors? Too bad, because I would encourage you to take Dr. Sanchez's seminar in wave analysis, because it just seems very applicable. I noticed that we have some of our music faculty here. Yeah. Professor Gibson, your comments on the presentation?
No, quite interesting, and yeah, I think you're right. There's a lot of parallels with the music industry people could draw from these.
You know, I couldn't get out of my head. You know, there were some of those mathematical formulas. What would Beethoven's Fifth Symphony look like if you put it into a mathematical formula? As I said, we have time for a couple of questions. Before we do that, we have one way back there. In fall semester, I was passed a note that Dr. Costa, who is here, will be giving our next lecture on chaos theory.
I suppose.
Yeah. Thank you very much. That was passed to me during the presentation. And one last thank you. Dr. Rakshak Adhikari is responsible for kind of coordinating things. The coffee and the cookies back there are his doing. So thank you. And the coffee's great. We have a question way back there.
Thank you, Dr. Sanchez. I'm Johnny Farrow. I teach in art and design. I work a lot in electronic music too. So the Fourier transform is a common like object in some of the programming that I do in that realm. Do you know about this software Maxim SP?
No. Sorry.
Yeah, I'd love to have coffee with you and talk more about this. But the question I had though is, I'm a sort of amateur science nerd, I guess you could say, and I see reports a lot of times about a black hole that is at the center of the Milky Way.
Yep.
I don't know if this is true, but maybe someone here who knows could confirm it. Maybe you can. But they say that the note that is coming from the center of the Milky Way, from that black hole, is a B flat, which I think is pretty funny as a note, generally speaking, because it has kind of a funny name. But I don't know. Do you know anything about that? Can you shed light on that?
No. certainly I cannot say what precise node is that thing, and I will need perhaps a little bit note exactly what this node is associated to, because when we see, when I was talking about these nodes, there is this phenomena of actually two black holes coming together. In the Milky Way, it's more like it is just there, but perhaps they are kind of trying to associate a wave to the rotation or something like this. But to be honest, I'm not sure. But if we have that coffee, I will do my homework and I will try to come with you with an answer.
Another comment. Reggie, excuse me. In our modern world, most of our music is digitized now versus being analog. How do you modify your approach to handle that?
To handle analog.
That is, discrete, quantized, sampled signals versus continuous.
Well, actually, for example, like I think what is in practice used is the discrete one, because if you want to do nice pictures like this, because the continuous one, you need like the whole signal ahead of time. And this is often not actually feasible, or computationally is very expensive, particularly if you want things. And that is why I think that everything has moved digitally, because you can really localize a bit both in frequency and in time. But well, I think that, well, yeah, you have some trade-offs, right? If you have analog kind of signals, then you can, or as I understand what you say, like, yeah, if you have a signal that is, you don't cut it into pieces, then, well, you will have a lot more of precise information about the frequencies and so on. But if you do it like digitally, like these chunks will kind of try to make a trade-off between frequency and time and so on. But then you will not be as good neither in time nor in frequency, because then you have made these chunks.
I guess what I'm really kind of asking about too is the use of the discrete Fourier transform and the fast Fourier transform versus the analog Fourier transform.
Yeah, and I think that is just a computational aspect of it, because, well, this one here actually requires, well, for example here, this required integration over an infinite amount of time. This often is numerically expensive, so people don't like it. And again, like for this to be, like the Fourier transform, if I just show you this one here, you have very little information when these frequencies are happening. And if you are here, then you don't know which frequencies are happening. So you do discrete and short Fourier transform, because exactly you want these both things, both information at the same time. You want time and frequency. And that is why most of the motivation about short Fourier transform and so on comes from this kind of wish to say, at this time is happening this frequency, which the Fourier transform can give you, but you need to weigh ahead of time the whole signal. And that is sometimes not so nice.
Let's give him a round of applause.